welcome back, everybody. Now we are, you see this scary word, theory. Well, technically, we are now moving on to the advanced part of the lecture. What we have seen so far, the relational algebra, the relational model, how to create tables with SQL, how to insert data, how to query data with SQL. This was all the basic part that is rather well known. Now, we are going to look into something advanced that is taught at the bachelor's level of computer science. It's part of the data management lectures in the first or second year. Actually, it's something we do a lot in Germany, in Switzerland, in the US, maybe a bit less, but Germany, Switzerland, there's always that that is taught. Of course, in the computer science bachelor's, we spend several weeks over that. There's a lot of very heavy theory, getting a lot into the details. I'm not going to give you all of the theory because it can get very complex. So I'm going to give you the most important aspects of it. I'll try to give you the visuals of that theory. But of course, I'll also explain to you why we have this theory, because this is actually useful. It's not just that people decided to do math for the fun of it. It actually is useful in reality. So we looked into tables that you saw they are also called relations. We looked at the relational algebra, which is a way to manipulate tables. So you know now selection, projection, aggregation, sorting, join, theta join, union, intersection, subtraction. So all these things that we can do with table called the relational algebra. So imagine that you set up a web shop. You put data in PostgreSQL, you add some PHP or Java codes or maybe JavaScript to produce your HTML pages, and you applied what we've seen to create your tables with your columns and your domains. You put data in there, and you start your website. It's the grand opening day, and then you run into problems. What are the problems that you could run into? Imagine that this is how you design your web shop. So you decided to create a table. You know how to do it in SQL, right? Create table, sales, product varchar, price numeric, customer text, quantity integer, city text, and that's it, right? That's the create table. So imagine that you put your data in there, and that's what it looks like. Maybe before showing you, does anybody see a problem with that design? This is actually not good design. It's not a good idea to set up a web shop like this. I will tell you, of course, but I want to give you a chance to spot any issues on Zoom. Nobody? All right. So here's the thing. You see that I'm selling phones, laptops, TVs. What's the price of the phone that I'm selling? Well, it's 800 francs, right? The price of the laptop is 2,000 francs. The TV costs 1,000 francs. And here, these are my sales. So for example, that phone for 800 francs was bought once by John, who is from Zurich. It was also bought twice, a quantity of 2 by Peter, who is in Bern. And it was also bought once by Mary, who is from Basel. John from Zurich, the same John that is here, bought 3 laptops. And Mary bought 1 laptop, the same Mary that was here, right, for 2,000 francs. And Mary, also again, the same Mary from Basel, bought 2 TVs for 1,000 francs, right? So, so this is where I store my data. Now, imagine that, I don't know, the data is getting old and I want to delete, I want to delete stuff. So imagine that I delete this row over here. So I want to delete the order of the phone by Peter. Do you see the problem? If you do that, you basically delete the information that Peter ordered the phone. But by doing that, Peter is gone. You don't even know that Peter is from Zurich anymore. So it means that if you delete the order, you also delete the customer. Who sees that? Right? So this is the problem. Here, imagine that you want to delete the order by Mary of the TV. So Mary also ordered other things. So you still know that Mary is from Basel. The problem is that in that case, you lose the information that the TV costs 1,000 francs. So if you want to sell it to somebody else, you forgot the price. You don't have the price anymore, right? So it's gone. So what you could do to try to fix it is to just say, okay, if I want to delete the information that Mary ordered the TV, I can just put nulls in there, but I keep the TV with 1,000 francs. But then you start to see that things become messy now, right? That's not clean. That doesn't look good, right? Plus, if you delete it again, you need to check if it's already there with nulls, because otherwise you'll have several times with nulls. So it becomes a huge mess, basically. So this is called a deletion anomaly, that issue. Another one is called an update anomaly. Imagine that you want to update the price of the phone. So imagine there's inflation, right? Maybe not that much in Switzerland, but still a bit of inflation. So imagine you update the price of the phone here, you make it 150. But the problem is that at other places, it's 800. So now the price is becoming inconsistent, right? And I'm not even mentioning the fact that there is the price for which you're selling it currently and the price at which it was ordered in the past and so on. So basically, there's a lot of things that are basically handled by this table, and it's too much for a single table, right? So the price is now inconsistent. We have a remark on Zoom. So if the point is to keep as much data as possible, why even consider deleting anything? Oh, so here there's other practical aspects. So there's the law, for example. So there was a period in which many companies were hoarding data just in case, because you might need it for future analysis. But now you know that you have data protection laws in Switzerland, you have GDPR in the European Union, so you are not allowed to retain data for longer than you need it, right? If at some point after a couple of years, customers might no longer interact with you, you cannot just keep that data forever, right? So you have at some point to delete things in the database. So it's a question more related to legal aspects. Does it make sense? Yeah, all right. Okay, so that's an update anomaly, right? So you now have an inconsistent price for the phone. So if you want to sell a new phone, then you don't even know if it's 850 or 800. What about insertion? Imagine that now I also start selling USB sticks. The problem is nobody ordered them yet. So I basically have to put my USB stick in the table with a price of 10 francs. But customer quantity city nothing, right? So do I put nulls? Do I put some default value, right? So you basically, again, have a problem here. The same, imagine a customer registers to your web shop, Bill from Lausanne, but Bill hasn't ordered anything yet. So you basically insert Bill and Lausanne, but what do you put for quantity and so on? So again, it's a mess. It's basically a big mess. I think you switched. What is going on today? There's just technical issues. Computer mic, no, it says audio web conferencing. Let me check. Maybe I increased the microphone or the audio. Can you still hear me if I talk far away? At least I can still see the audio icon that is lighting up. Can you still hear me on Zoom now if I speak? I'm very far away from the computer. Yes, that's a yes. So now it's even too loud, maybe. Oops. For the feedback effect, keys are yes, going to initiate a bit. Okay. All right, so this is an insertion anomaly. So basically, the problem we have here, if we just describe it with waving our hands, because we do it mathematically, but if we describe it waving our hands, that table is storing too much. It stores products, it stores customers, it stores sales information, and so on. That's too much. You shouldn't put all of that in the same table. The correct way to do it is to have separate tables. This is what is done in reality. So you have a table for the products, you have a table for the sales, you have a table for the customers. And of course, we studied primary keys and foreign keys. So you basically have these relationships between the tables where you have customer ID. So here I simplified using the first names, but of course you would have customer IDs in reality. So John, Peter, Mary, Bill. This is foreign key pointing to that primary key. You remember foreign keys with the references in SQL. So this column is pointing to the customers here. Product here, of course, in reality, you would have a reference number, not the name of a product, but I simplified a bit. This here is a foreign key that points to the product here. And basically that sales points to a product, points to a customer, and specifies the quantity that they bought. You might also have a date and so on and so on. So this is a much better design in reality. And this is how it's done. And in a real production database system, you therefore have many, many different tables that are nicely tied together with these foreign keys. And then in SQL, you use the joins in the from clause to connect these tables together. Who is with me? All right. But now we need to answer that formally, because here I was just waving my hands. Like it's too much for a single table. We need to split it into tables. But what's the math behind that? And the math, the goal of database design theory is to tell us what it means to have a better schema. This is database design theory. So database design theory has a lot of different concepts that I will introduce to you one by one, give you an intuition. I'm going to just list the names here, just now, what we are going to look into. We are going to look into the concept of functional dependencies, super keys, candidate keys, primary keys, prime attributes, first normal form, second normal form, third normal form, Box-Coid normal form, fourth normal form, fifth normal form, sixth normal form. It's like music, right? It sounds a bit like music. So these are basically just mathematical constraints on the tables that tell us what is desirable in this schema design and what is undesirable in schema design. So the rest of today and probably next week, I'm just going to throw all of that math at you. Of course, I'll take it slowly, making sure that you're following me and so on. But this is the menu for today and next week. I'll start with the first normal form. I have good news for you. You already know the first normal form because I gave it to you under a different name already. In fact, you might remember that we defined a relational table as a collection of maps, right? More specifically, that collection can be a set, a bag, or a list. So it can be a set of maps, a list of maps, or a bag of maps. Let's take sets of maps for the purpose of database design theory, right? So a relational table is a set of maps, but it's not just any set of maps. I have these constraints, remember? Relational integrity, domain integrity, atomic integrity. Relational integrity means they all have the same attributes, all of these maps. Domain integrity means that every column has the same data types, on the integers, on the dates, and so on. And the third one, atomic integrity, do you remember what it means? Yes? Exactly, like in Inception. You don't have a table in a table in a table. This is atomic integrity. Well, in fact, atomic integrity is also known as first normal form, right? So you already know what it means. This here doesn't fulfill atomic integrity. We also say it is not in the first normal form. So the first normal form is the requirement that you cannot have a table in a table in a table, all right? So you see why it's not in the first normal form. It's not, doesn't have atomic integrity because here I have a list. That's not something atomic, so that's not okay, right? So this type, technically it's allowed in PostgreSQL, but if you use that, you're not in the first normal form. Right? Everything clear? Technically, I didn't teach you anything new except that I gave you a different name for atomic integrity, right? That's all I really did here. This is another example. You can also do it in PostgreSQL. You can actually have JSON in the columns. For those who know JSON, these are maps or lists. But this is also not, this doesn't fulfill atomic integrity, so this is not in the first normal form. This is also not in the first normal form. We have tables in tables, right? So it's also not okay. This is also not okay. So just counter examples here. This is also not in the first normal form because we have tables in tables. So really, what we require in the first normal form is that when we say we have sets of maps, these maps map strings to values. In the first normal form, these values must be atomic. Atomic means strings, numbers, dates, and so on, but not tables or lists or anything that has a structure. This is atomic. This is in the first normal form. How do I see it? Look at the domains. It's strings, booleans, integers. That's all good to me, right? That's all in the first normal form. So as long as everything is atomic, this is in the first normal form. So this is what it means. It's a plain relational table. It's flat. There is absolutely nothing nested in there. No nested tables, no nested structures. So you forbid that sort of things that would break the first normal form. And this is an example of first normal form. You see it's nicely flat, could fit in a spreadsheet software very nicely. Okay? Now, there is something that we usually also associate with normal forms. So a normal form, as I said, is a constraint on a table, like the first normal form is a constraint that it's atomic. But typically, when you define a normal form, you also specify a way to force a table that is not in that normal form to be in that normal form. So it's an algorithm that transforms a table that wouldn't be in the normal form in such a way that it becomes in that normal form. This is what you have on the screen. On the left, you have a table that is not in the first normal form because the third column has nested tables. And the trick to transform the table into a table that is in the first normal form is to take these values here and duplicate them. Basically say phone 800, you duplicate it 3 times and put it in here, and in here. Laptop 2000, duplicate it twice, here and here. This you duplicate, you put it here, and here you just add nulls. This is what you get, right? So you agree that the one on the right is in the first normal form, right? I can put nulls in there, the question marks, I can just fill them with nulls, but this is in the first normal form. So you agree that the data that is on the left and on the right is the same data, right? There's no difference, right? I just duplicated what wasn't as a table and put it in there. So what you see on your screen is the technique to take a table that is not in the first normal form because it has nested tables like this. You assume there is some structure in the tables. And all you need to do is to duplicate the values of the tables that would otherwise be atomic in such a way that you get what there is on the right, okay? And then you are on the first normal form. Now, we already know that's not enough because the table that is on the right, I already showed you all the problems that it has. And this is why we have a second normal form, a third normal form, so many, many other constraints that we add on top of that. But at least it's a first step, right? You at least start with this. Okay, so this is the first normal form, plus how to turn a table that is not in the first normal form into a table that is in the first normal form. There is a concept that I need to introduce before I talk about functional dependencies and superkeys and so on. It's the concept of a table universe. The name sounds scary, but it's really not scary. It just means that tables have a life and change over time. That's really what it means. So if you have a table like this, that would basically be a snapshot of your web shop at a specific point in time. But the thing is, you have a website, people connect to that website, they place orders, they register, and so on and so on. So that table changes over time, right? It evolves. You insert, you delete, and so on. So it's not a fixed thing, right? It evolves over time. But there is one thing that doesn't change, it's the schema. So when you enter this create table, blah, 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 with the columns and the domains, that doesn't change. Or at least it doesn't change often, right? Typically, you try not to touch it, because every time you touch it, it's actually heavy to do, and you can easily make mistakes. So let's assume we don't touch it. We don't touch the schema. We don't touch the columns. We don't touch the domain, but we still allow for the data in there to evolve. You can insert tuples, delete tuples, modify the tuples, as long as they still fulfill the schema. So there is this assumption that PostgreSQL or any relational database management system is going to monitor and check that as this table lives its life and evolves over time, that it never breaks the rules. So you can only change it as soon as it respects the schema. So these are the integrity constraints defined by your create table statement. They must hold at all times. What we call a universe or a table universe is the absolutely gigantic set of all possible contents that the table can have according to the schema. It's huge, right? That's gazillions of possibilities in there. It's all the valid, called an extension, all the valid contents that the table can have, right? So there's 3 examples in there, but it's mathematically absolutely enormous. And so the idea is really that this is a Venn diagram that we have this big rectangle outside has the set of all possible sets of maps that you can have. Then you add relational integrity, you add domain integrity, you add atomic integrity. So here you have all the relational tables. And then you might add a schema and further constraints like check, unique, non-null, and so on. So you further constraint. So that would be the multiverse containing any possible sets of maps, and then you reduce with constraints, you know, to restrict what you can have. So one way to restrict is to specify attributes and domains and so on to request that it's atomic, and we'll see other ways. A functional dependency is also a way to put a constraint on the content of the table. The higher normal form, the second, third, Boyce code, and so on, also corresponds to constraints like that. So this is the way to visualize many of the things we see today. They are just really constraints on what tables can look like. It's a yes/no answer that you give it. Does that table fulfill that constraint or not fulfill that constraint? For example, if you're considering the relational integrity, the table that you see on the right is not part of my table universe, the one that I considered with my schema. Why? Because my schema specifies 4 columns, but what I have on the right only has 2 columns. So it's not part of my extension. It's not allowed. PostgreSQL will not let you have that. This is also not allowed because this one is breaking domain integrity, right? The second column is supposed to be a numeric, but what I have outside my universe on the right, foo bar, these are not numbers. This is also not allowed. This time it's domain integrity. This table on the right, I basically would like to disallow it. I would like to disallow it. Why do I want to disallow it? Because I would like for the phone prices to be consistent. Here it's 800, 850, 900. I would like to disallow it. But how do I disallow it? Not with relational integrity, there's nothing wrong in there. Not with domain integrity, there's nothing wrong in there. Not with atomic integrity, there's nothing wrong in there. So I need something else to be able to specify that I don't want that. That something else is a functional dependency. And more exactly, a functional dependency between the name of the product and the price. And this is what I'm going to now describe. So functional dependencies. Here's math that I'm throwing at you. Don't be scared. So basically, in order to define a functional dependency for a specific table that I'm looking at, I need 2 sets of attributes. For example, ABC and DEF, right? But let's call these sets S and T, right? Again, S and T are not attributes, these are sets of attributes, right? Several attributes. So when do I say that T is functionally dependent on S? So the set of attributes T is functionally dependent on the set of attributes S. That is the case when, if I take any 2 records of my table, so T1, T2, T for tuple, right? Tuple, record, row, it doesn't matter how we call them. We take 2 records in the table. It must be, for this to be true, that if my 2 tuples match everywhere for the attributes in S, so they all agree on S, then they must also all agree on T for all attributes in T, right? This is an implication. And if that's true, that if any 2 tuple in the table, when they agree with S, they agree on T2, then I'm allowed to write this here, S and an arrow and T. Now it's a bit abstract because S and T are technically sets, so I redid the same thing, but replacing S and T with actual sets of attributes. I took 3 attributes in each, but as you can imagine, there's no constraint on that. Can be 2, can be 0, can be 10, doesn't matter. It doesn't need to be the same number of attributes on the left and on the right either, right? You could have 3 on the left and 2 on the right. But anyway, so I'm taking 2 subsets of attributes, A, B, C, and D, E, F, assuming that my table contains these attributes. And basically, I'm saying that ABC functionally determines DEF, or that DEF is functionally dependent on ABC. It's just the same thing with the arrow. That is the case is for any 2 tuples that I take in my tables. If they agree on A, B, and C, which I see here, it means that T1 and T2 agree, they have the same values for A, B, and C, then they must also have the same value for D, E, and F. That is a functional dependency. Who understands that? I don't see any raised hands. Okay, that's fine because I have visuals and pictures. So here's my visual and picture. So I took an example here with different attributes in there. I have AB basically functionally determines DE, or DE is functionally dependent on AB. Visually, it looks like this. Whenever I have two records in my, imagine a billion rows in there, and I randomly pick two records, these two, you agree they match here on A and B, these two records, this and this, right? They agree on A and B. But because if I want to enforce this, then if they agree on A and B, you must have that they also agree on D and E, right? So here, that's totally fine. This is consistent with this dependency, right? If you have foo and bar, then you must have true and one. The same goes here. It's just different records with different value. They agree on A and B, right? They have the same values. Then they must also agree on D and E. That's what it means. Now, a counterexample. This is a counterexample. In that case, that is broken. That is not true. This here does not hold for this table. How do I see it? Well, it suffices to find a counterexample. If you find two records in the table that agree on A and B, but they disagree on D and E, that's over. You have proven that this is not fulfilled. For the functional dependency to be fulfilled, it must be true for any two records. And for it to be broken, it's enough to find two records that break it. That's all. Just find two records like this. That's enough to prove that it's not true. Is there a question?
Yes. So could we have true and one also for bar and for bar?
Yes, absolutely. Absolutely. That's totally fine. Right? All we are saying is that if it matches on A and B, it matches on D and E. You could absolutely have the same values for D and E, even for different values on A and B. That's totally fine. Right? If I want to use a scary mathematical name, the function might not be injective, and that's fine, right? So now we have a break, and then I'll continue to scare you with even more concepts of database design theory. So see you in 15 minutes.